Okay, so let us now start the exercise set at the end of section 5.3. So in the first one we have to prove proposition 533, which if you recall is the proposition that tells us that the relation of two sequences of rational numbers being equivalent is an equivalence relation. That is, the relation we have to show that it's reflexive, symmetric and transitive. So let us start the solution. Reflexivity and symmetry follow directly from the definition of equivalence, that is the first definition. Why is that the case? You see, we say that two sequences of rational numbers an and bn are equivalent if for any positive rational number epsilon the sequences are eventually epsilon closed. That means for any such positive rational epsilon there exists a positive integer n such that the distance between the nth terms of the sequences is less than or equal to epsilon for all n greater than or equal to n. When this happens, we say that an and bn are equivalent. Okay. Now we want to prove reflexivity requires us to show that an is equivalent to an. So if you have the same sequence, then clearly this is true. In fact, in this case, since all these differences are equal to 0, you can, if you want, you can choose n to be 1 also, capital N to be 1, because all such terms are equal to 0. So all such distances are less than or equal to epsilon. In fact, strictly less than epsilon. So that's why an is always equivalent to itself, and that is why the definition of equivalence is, or rather that relation that this definition produces, that relation is reflexive. That's why we are saying reflexivity follows directly from this definition. Now what about symmetry? If say we are given that an is equivalent to bn, then this will be true. Here however you cannot necessarily choose capital N to be 1, that is not the point. But then if you want to claim that bn is also equivalent to an, then a similar condition should be true with an and bn swapped, interchanged. But that is easy to see from here itself, because inside absolute value you can change the sign. Instead of considering the rational number an minus bn, you can consider its negative, which is bn minus an. So this tells us that bn is, the sequence bn is also equivalent to an if an is equivalent to bn, and hence the definition of equivalence, that relation is symmetric. So we need not be concerned about these two things, at least reflexivity and symmetry, more than just mentioning that they are true. Now we come to transitivity. Here we need to argue, for transitivity we need to argue a little. Okay, Now let an, bn and cn be sequences of rational numbers such that an and bn are equivalent, and bn and cn are equivalent. Okay, now our aim is to show that an and cn are equivalent. So for that we choose any rational number epsilon greater than 0. Equivalence of an and bn gives us a positive integer n1 such that the distance between an and bn is less than or equal to, for convenience in place of epsilon we are choosing epsilon divided by 2 for all integers n greater than or equal to n1. Like that, equivalence of bn and cn gives us a positive integer n2 such that the distance between bn and cn is less than or equal to epsilon by 2 for all integers n greater than or equal to n2. Okay. Now we are going to make use of these two conditions to draw a conclusion about the distance between an and cn. And you can by now you can almost see, I guess, what we are going to do here. Choose a positive integer n3 greater than the maximum of n1 and n2. Such a positive integer can always be chosen then for any integer n greater than or equal to n3, we have distance between an and cn. This can be written as an minus bn plus bn minus cn. Now you use triangle inequality. An minus bn plus bn minus cn. Now note that since n is greater than or equal to n3 and n3 is greater than n1, so n will be greater than or equal to n1, and hence, I needed to write n1 here, and hence for that n, this inequality will be true, that is this distance will be less than or equal to epsilon by 2. So the first term in this sum does not exceed epsilon by 2, and like that the second distance also, second term also does not exceed epsilon by 2, because when n is greater than or equal to n3, since n3 is greater than n2, n will be greater than or equal to n2 as well, and because of that this inequality is also true, and together they give us epsilon. So you see that for all integers n greater than or equal to n3, this distance is less than or equal to epsilon. So that tells us that the sequences an and cn are eventually epsilon close, and since that is happening for any positive rational epsilon, so an and cn are equivalent. This shows that an and cn thus the relation is transitive. And this completes the solution. It actually completes the proof of proposition 533. Now I think I don't remember clearly whether these sequences an, bn and cn are actually there in the statement of this proposition, because here we have chosen them ourselves in the proof. It may be the case that already 3 real numbers are given for which we found Cauchy sequences an, bn and cn, whose formal limits are these real numbers respectively, and then we are trying to prove that x is equal to x. If x is equal to y, then y is equal to x, and if x and y are equal and y and z are equal, then x and z are equal. If that is the case, then an, bn and cn are already available to us. And one more thing you can see, that in this proof we have not used anything about the fact whether these sequences are Cauchy sequences or not. We just used equivalence of the sequences, that's all. So if that is the case, if an, bn and cn are already available, then you interpret the proof like that. There is no need to assume them separately. In any case, the ultimate structure of the proof is same. Okay, then we tackle the next one. Prove proposition 5, 3, 10. Hint, same hint again. Proposition 437 may be useful. Okay, in this proposition, the aim is to show that multiplication of two real numbers that we defined is well defined. That means, suppose you are given two real numbers x and y, which say are formal limits of two Cauchy sequences of rational numbers. One of them is an and the other is bn. Then, according to our definition of this product xy, it's the formal limit of the Cauchy sequence whose terms are a and bn. Oh, no, I cannot say that it's a Cauchy sequence. That's what I have to prove. So there are two things to prove here. The first thing is that we need to prove that the sequence given by these terms is a Cauchy sequence, so that its formal limit exists according to our definition of real numbers themselves. And then we need to show that if there is another equivalent Cauchy sequence an prime such that the formal limit of an prime is also equal to x, that is, the same real number is being given by two equivalent but different, maybe possibly different Cauchy sequences. That is possible, we have already seen. Then these two product is xy, but in one of them we use the Cauchy sequence an, and in the other we use the Cauchy sequence an prime. These two give us the same answer. So our choice of the Cauchy sequence whose formal limit is the given real number does not affect the calculation, does not affect the product. So once we prove this one also, then we can say that multiplication is well defined. So that's what we need to do here in this solution. So let us proceed with the tasks one by one. First, we show that the sequence an bn is Cauchy. For this we need to, the starting is same, you choose one rational epsilon positive and then you try to show that there is a positive integer for which so and so things happen. So choose a rational epsilon greater than 0. Okay. Since the original sequences whose formal limits are given, that is x and y, say, are Cauchy, so they are bounded. This we have already proved before, that if you have a Cauchy sequence of rational numbers, then it must be bounded also. Thus, there exist positive rational numbers k1 and k2, say, such that the absolute values of all the terms of the first sequence, they are less than or equal to k1, like that the absolute values of the terms of the second sequence are less than or equal to k2, and this will happen for all the terms, for all positive integers n. Okay, boundedness gives us these inequalities. Now, since okay, we already have chosen epsilon. Now, since an comma bn are Cauchy, there exists, just like before, positive integers n1 and n2 such that the distance between an and am, because we are going to write the condition for Cauchiness, so we have to take different terms from the same sequence. The distance between an and am is less than or equal to. Now here we choose the number somewhat cleverly. We consider it to be epsilon divided by 2k1. There are reasons for this choice. It will become apparent, and you can almost guess why we chose this thing, because in our final calculation, where we will be trying to estimate the distance between ANBN and AMBM, because we need to show that this sequence is Cauchy. In that calculation, this type of choice will be useful, such that this for all integers n greater than or equal to n1 and the distance between not just n, since we have m also, for all integers n and m greater than or equal to n1, and the distance between bn and bn is less than or equal to epsilon divided by 2k2 for all integers n and m greater than or equal to n2. Note that these choices can also be made. That's because k1 is a positive rational, so epsilon divided by 2k1 is also a positive rational, for which we can write this condition like that for this one also. Now choose a positive integer n3 greater than maximum of n1 and n2. Okay, for all integers n and m greater than or equal to n3, we have need some ink. We have, so we start with this difference an bn minus am bm. Okay, now what we do inside, we introduce a new term, and that new term is an bm, that is an bn minus an bm. But because we introduced a new term, we have to write, let me just write this term there. This is equal to an bn minus an bm, so we have to add that also to balance things, minus am bm. Okay, now this becomes equal to, if you take an common out from the first two terms, you get bn minus bm, plus if you take bm common out, you get an minus am. So now if I use the triangle inequality, then first I will get this. And then this thing is equal to, using further properties of multiplicativity of absolute value. If you have the absolute value of a product, that is equal to the product of the absolute values. Okay, now we come to the question of how these terms are bounded or what their upper boundaries are. Absolute value of an is less than or equal to k1, and that fact is independent of n. For all n, that is true. So this will be less than or equal to, I think I need to change these things, make this 1 and this one 2. That also I can do. I mean, for this choice also we will get some positive integer n1, and for this choice we will get some positive integer n2. Now you see that because n and m are both greater than or equal to n3, so they are both greater than or equal to n2 also, because n3 is greater than n2, and so this second set of inequalities is true. So that means this difference, this distance is less than or equal to epsilon divided by 2k1. Similarly, this one is less than or equal to k2, and this distance is less than or equal to epsilon divided by 2k2, and this turns out to be equal to epsilon. That means for all integers n and m greater than or equal to n3, this distance between an bn and am bm, that is less than or equal to epsilon. So that just tells us that the sequence an bn is a Cauchy sequence. So this is a Cauchy sequence. Okay, so the one half of the solution is over. Now we move to the next half. Let an prime be a Cauchy sequence of rational numbers such that its formal limit is also equal to the formal limit of an. Or in other words, by the definition of this equality, the sequence an prime and the original sequence an are equivalent. And now we have to prove that the formal limits an prime bn and that of an bn are equal. That is, those two sequences are also equivalent. That is, we need to show that this sequence and this sequence are equivalent. That means we need to show that if any positive rational epsilon is given, then they are eventually epsilon close. That is, the distance between their nth terms is less than or equal to epsilon. Okay. Now if you consider such a distance, in fact that's how we guess about what to take here. We want to make this less than epsilon, and this turns out to be equal to an prime minus an times bn. So from here you can see that you have to use the bound that the sequence bn has, along with the fact that this is true, that is an prime and an are equivalent. So this can be made small, and for this already there is a bound. Okay, so that's how we are going to proceed. choose a rational epsilon greater than 0 since an comma an prime are equivalent there exists a positive integer k such that the distance between an and an prime is less than or equal to epsilon divided by k2 for all n greater than or equal to k. Okay, this is coming from the equivalence of these two sequences. So far, any integer n greater than or equal to k, we have an bn minus an prime bn. This is equal to an minus an prime. We are writing directly times bn. Now the first distance is less than or equal to epsilon divided by k2, and the second factor, that absolute value is less than or equal to k2. So this becomes equal to epsilon. Thus these two sequences are equivalent. Hence, their formal limits by definition are equal. So this proves that multiplication of real numbers is well defined. In fact, there is another thing to prove here, namely if the second sequence bn is say equivalent to some other sequence bn prime, then also the multiplication is not affected. But actually there is no need to do that in this case, because multiplication is commutative, which follows easily from the definition of multiplication itself. So by what we have proved, that thing also has been proved. So the solution is complete. Okay, now next exercise 5.3.3. Let a, b be rational numbers. Okay, show that a is equal to b if and only if the formal limit of this constant sequence A is equal to the formal limit of the constant sequence B. That is, the Cauchy sequences are equivalent this and are equivalent if and only if A is equal to B. This allows us to embed the rational numbers inside the real numbers in a well-defined manner. In a well-defined manner. We have already discussed about this embedding. This solution is quite easy. If A is equal to B, then we obviously have this thing. Why? If A is equal to B, then these two sequences are actually the same sequence. So their formal limits will also be same. And why is that so? Note that it's not simply because they are the same sequence, but actually it's because of the fact that equivalence of two sequences, that relation is reflexive. So if you have a Cauchy sequence AN, another Cauchy sequence same AN, then since they are equivalent, so that's why their formal limits are equal by the definition of equality of real numbers. So this part is obvious. Conversely, assume conversely we assume this, then the sequences are equivalent So for any epsilon greater than 0, there exists a positive integer, say m, such that the difference between the nth term of the first sequence and the nth term of the second sequence, the absolute value of that difference is less than or equal to epsilon for all n greater than or equal to m. But the thing here is that all such differences are equal. If you calculate the difference, this distance for these two sequences, where say an denotes the first sequence and bn denotes the nth term of the second sequence, then for all n it will be equal to this rational number, and that's why for all n greater than or equal to m. This may look somewhat strange because this one does not have any n, but in a sense it has. It is considered as, let's just write here is the absolute value of the difference between the nth terms of the sequences and this. Okay, now note that for any rational epsilon that is positive, this difference has to be less than or equal to epsilon, and you can change epsilon, you can make it however small you want, still this quantity has to be less than or equal to epsilon. And this is the time we refer to one of the results about absolute values and distances that we proved when we developed the system of rational numbers. So from this inequality, since is arbitrary, proposition 437a Proposition 437 has many parts. Each part says something about the absolute value function and distances between two rational numbers. So that part A, you go to this in the 4th chapter, you will see that this implies A is equal to B. Okay, A has to be equal to B because actually what it does imply is that this rational number must be equal to 0, but then by the properties of absolute value, an absolute value is equal to 0 if and only if the number inside is 0, that is if and only if A is equal to B. So this completes the solution. Then two more are there, 5, 3, 4. Let A and be a sequence of rational numbers which is bounded. rational numbers which is bounded. Let Bn be another sequence of rational numbers which is equivalent to An. Show that Bn is also bounded. Okay. Choose a rational epsilon that is positive. Now what is given is that An is equivalent to Bn. That means for this epsilon, An and Bn will be eventually epsilon close, since these are equivalent they are eventually epsilon close. So we can now use an exercise from the previous section. Thus, by exercise 5.2, boundedness of An implies that Bn is also bounded. You go and look at this exercise, you will understand what has happened here. So that's how we get the fact that Bn is bounded. And the last one is this. Show that the formal limit of the sequence 1 by n is equal to 0. We already know, we have already proved in a previous result that the sequence 1 by n is actually a Cauchy sequence. So we are going to recall that fact. We have already proved in proposition 5.1.11 that this sequence is a Cauchy sequence. So that means to prove that its formal limit, Cauchy sequence means its formal limit can be considered according to our definition of real numbers. Now we need to prove that this formal limit is equal to 0. Now think of the embedding that we talked about, embedding of the system of rational numbers into the system of real numbers. According to that embedding, this real number 0 is actually equivalent to the formal limit of the Cauchy sequence 0, where all the terms are the rational number 0. Okay, so we need to actually prove, this means we need to prove these two formal limits are equal. In other words, we need to prove that that Cauchy sequence is equivalent to the constant Cauchy sequence of rational numbers where all the terms are equal to 0. So that's what we are going to do now. So it's enough to prove that the sequences 1 over n and 0 are equivalent. Choose a rational epsilon that is positive, then there exists a positive integer n greater than 1 over epsilon. The existence of such an n comes from the result with this number 441. I can't exactly remember if it's lemma or theorem or proposition. I think it's lemma. You go there and it's that result that tells you that for every rational number x there exists exactly one integer n such that n is less than or equal to x and x is strictly less than n plus 1. And in fact this n we called the integer part of x. In that lemma you will see that for every rational number you can choose a positive integer that is greater than that rational number. So there is no largest rational number. It's that result that we have used here. Now our positive rational number or our rational number is this 1 over epsilon. Okay. So for that also we can find a positive integer that is greater than 1 over epsilon. let us now see what we can do with this capital N. Then for all integers n greater than or equal to capital N, we have one over n minus 0. This is 1 over n. This becomes less than or equal to 1 over capital N. You take reciprocals on both sides and you get the inequality is reversed. The same thing happens here. Since n is greater than 1 over epsilon, 1 over n will be less than epsilon. So you see that we have proved that for any positive rational epsilon, the sequence 1 over n and 0, they are eventually epsilon close. So that means they are equivalent. This proves that 1 divided by n and the constant sequence 0 are equivalent. So that's what we wanted to show, which implies that this formal limit is equal to 0. So that completes the solution and that completes this section also. After this, in the next section, that is going to come in the next analysis video, we are going to put an order relation on the set of real numbers, which will allow us to say that this real number is greater than that real number. That thing we are going to do next. So with this, I end this video. If you have any doubt or you want to discuss anything regarding this section or anything else regarding mathematics, then you can comment in the comment section below. So that will be all for tonight. Signing off, this is me, Lucifer, from A Mathematical Room. Have a nice night.